who is going to comment ex parte. Okay? So Courtney, if you would give us just a couple minutes about yourself and where you're going, and then your presentation, that would be great.
All right, well, thank you guys all for coming. Big room. I'm Cortney Crane. I got my bachelor's degree at Emory University in physics, and then I came straight here to get my PhD. And that's what I've been working on for the last 5.5 years. And when I graduate, I'll be working for Exponent, which is a consulting company, failure analysis consulting company back in Atlanta. So with that, I'd like to start by presenting to you some of the work I've done on my dissertation. And the title of my talk today is Validation of the Coupled Dissolution Hydrogen Embrittlement Mechanism of Intergranular Stress Corrosion Cracking in Low Temperature Sensitized Aluminum Alloy 5083 with H131 temper. Okay, to start, I just want to give you a nice overview of where we're going. I'm going to start off giving you a background of the aluminum magnesium 5000 series alloys and how they sensitize. And then we're going to focus on this question, and that is, what is the effect of low temperature, low sensitization on stress corrosion cracking? And to do that, we're going to use this approach. First, we're going to characterize intergranular stress corrosion cracking as a function of sensitization. Then we're going to use that data to hypothesize a mechanism for intergranular stress corrosion cracking. Then we'll validate that mechanism. And finally, we'll generate a framework so that we might be able to predict the crack growth rate. And of course, we'll finish with some conclusions. All right, to start off, 5000 series alloys are aluminum magnesium alloys. And they're solid solutions strengthened by their magnesium content, which gives them moderate strength, lightweight, and a great substitute for steel. So they've been used in a lot of the next generation naval structures. The problem is when you have more than 3 weight % mag in the alloy, you become susceptible to sensitization, which causes or leads to intergranular corrosion and intergranular stress corrosion cracking. Now, as you can see, our alloy down here, 5083, H131, has 4.4 weight % mag. So we are definitely susceptible to intergranular corrosion and intergranular stress corrosion cracking. The other thing that's important to note is that the way the plate is rolled and forged, you have a grain structure that leads to mixed mode cracking. So you might have a crack that starts in this direction and then changes to this direction along the grains. So what is sensitization? Well, sensitization occurs when your magnesium diffuses to the grain boundaries and causes the precipitation of a beta phase, which is an aluminum-3 mag2 particle. This particle is mainly on the grain boundaries, and it can form at 40 to 230 degrees C. So all the surface temperatures in service could cause this sensitization. Now, we like to use high temperatures because that's easy to cause sensitization in the lab. The problem is when you sensitize at temperatures above 100 degrees C, you'll get a connected grain boundary beta morphology. Something that looks like this. All of your grain boundaries are coated in this beta phase so that you have a very easy crack path that's continuous, well, semi-continuous, for intergranular corrosion and intergranular stress corrosion cracking. So what we wanted to focus on was low temperature sensitization, where you'll have a more discontinuous precipitation of the beta phase. And so that might look something like this on the grain boundaries. You have these small particles that are separated, and these cause a different mechanism. These could cause a different mechanism for intergranular corrosion and intergranular stress corrosion cracking. So the connectivity and the distribution of beta is what controls intergranular corrosion and stress corrosion cracking, and it has not been investigated. So the first thing that we need to do is characterize this degree of sensitization, or this DOS level. And to do that, we use this nitric acid mass loss test. This mass loss test is ASTM G67, and what we do is we throw a piece of 5083 or an aluminum magnesium alloy into nitric acid and let it sit there for 24 hours. Then we take that piece out and we measure how much mass was lost. Nitric acid preferentially dissolves beta phase. So the mass loss can be attributed to the beta phase that was in your microstructure. So I plotted this mass loss measurement versus our sensitization time at 3 different temperatures. And you can see at very high temperatures, you get very fast sensitization that quickly rises to high DOS measurements. But when you have these low temperature sensitizations, it's much more slowly, you get a much more slow mass loss increase. So these are the 3 temperatures that we'll be looking at, and these are all the conditions that I'll be looking at to characterize intergranular stress corrosion cracking in this work. All right, well that brings us to our problem. What is the effect of low temperature and low DOS on intergranular stress corrosion cracking? Well, published literature has looked at intergranular stress corrosion cracking for a lot of aluminum magnesium alloys. But we're limited, this data is limited because no one has been able to quantify the effect of low temperature sensitization on intergranular stress corrosion cracking, particularly in the orientation along the grains, and correlated with the beta size, spacing, and morphology on the grain boundaries. So once we have this characterization, we might be able to inform and validate an interactive crack tip dissolution and hydrogen embrittlement mechanism. And we also might be able to predict the impact of intergranular stress corrosion cracking on structural integrity and maybe evaluate fixes or ways to mitigate intergranular corrosion and stress corrosion cracking. Okay, so now that I've gone through our background on the question, I'm going to move on to our approach. And the first thing I want to do is characterize the intergranular stress corrosion cracking as a function of sensitization. To do this, I used a subcritical crack growth experiment. I used a single-edged notch tension specimen with the crack growing in the L direction, so along the grains, the worst case scenario for cracking. Then I put a fatigue pre-crack in air to get a sharp crack tip, loaded the specimen in sodium chloride, and applied a polarization that was near the open circuit potential. And then I loaded it at a very low load for 10 hours to see if I could measure the intergranular corrosion. And then right after 10 hours, I started to increase the displacement rate at a constant rate until the specimen failed. And during this entire time, I was measuring the crack growth rate with a high resolution direct current potential drop method. So typical results look something like this. I have the crack growth rate on the y-axis, the stress intensity on the x-axis, and the resolution limit of our system in the gray. This particular data set was for a 58.3 H131 specimen that was sensitized at 100 degrees C for 175 hours, giving a mass loss of about 22 milligrams per centimeter squared, so right in the middle. And you can see the stages of my test here. So we have very low crack growth rates at very low stress intensities. So this stress intensity can be thought of as the driving force for crack growth. As you increase that stress intensity, your crack growth slightly increases, but it does not increase rapidly until about 10 or 11 MPa root meter. And this is what we call the threshold stress intensity. So this is normally due to a combination of chemical or mechanical driving forces that causes the rapid crack growth here. Everything before this is likely intergranular corrosion, but not cracking induced. Excuse me, my drink. So once you get to your threshold stress intensity, you meet stage 1, stress corrosion cracking. So this stage 1 and stage 2 is typical of all stress corrosion cracking. Stage 2 is usually due to your hydrogen diffusion limited crack growth rate. So we can use a stress intensity. I particularly use 15 MPa root meter for this data set, and the threshold stress intensity to quantify all stress corrosion cracking in this alloy. So if you remember threshold stress intensity and stage 2 crack growth rates, I plotted both threshold stress intensity, stage 2 crack growth rates, for all of the sensitizations that I looked at. And you can see on the left here, when you have a very low degree of sensitization, very low either temperatures, times, or mass loss measurements, your threshold stress intensity is within the region of your fracture toughness. So it's as if you're not even in sodium chloride, you're breaking as if you were in air. Once you increase that DOS level, you can see that you drop the threshold stress intensity severely until a point about 10 milligrams per centimeter squared, DOS level, where you start to see the step function and your threshold stress intensity continues to decrease at a unique function of DOS. And now the important thing to note is that we did this for 3 different temperatures, and all 3 of these temperatures fit this correlation. And the same thing can be seen for the crack growth rate. At low crack growth, or at low degree of sensitization, your crack growth is very low. This arrow represents your resolution limit. As you increase the degree of sensitization, your crack growth takes off, and then it levels out, but continues to increase with further sensitization. So this DOS level is very important for stress corrosion cracking in this alloy, in this environment, NaCl at -0.8 volts. So we need to figure out why this might be happening. And what we believe is that the distribution of beta is controlling this threshold. So there's been a lot of studies that have looked at the grain boundary beta precipitation for several different temperatures and times. And this particular study was looking at TEM analysis. And they found that when you age these specimens at different temperatures and different times, you'll get different morphologies of beta. So in particular, at low temperatures and times, you'll get widely spaced precipitates. Something that looks like this. You have beta here, and then you have the grain boundary between it, and they're very widely spaced. Once you get close spaced beta, which is here for 175 degrees C for 50 hours, you might have a more connected beta morphology on the grain boundaries. So what's interesting is this line right here between the widely spaced precipitates and the closely spaced beta roughly correlates with 10 milligrams per centimeter squared. So that could be a reason why we're seeing this threshold stress intensity at 10 milligrams per centimeter squared. Now another study was able to open up the grain boundaries of 5083 with a liquid gallium embrittlement mechanism, and so they were able to see the actual grain surfaces and look at all the particles that were on the grains. So they characterized these particles by the size and the spacing, and were able to find, or put together this ratio of the nearest neighbor distance and the equivalent diameter, the spacing over the size, and they saw that at 10 milligrams per centimeter squared, there was a nice drop in the ratio, which was mainly due to the size of the precipitates increasing. So again, at 10 milligrams per centimeter squared, there could be a correlation with the size, the spacing, or the morphology of beta phase. So quick takeaway point to that section. Stress corrosion cracking susceptibility quantitatively correlates with the G67 mass loss or the DOS measurement, and stress corrosion cracking can be eliminated for a DOS less than 10 milligrams per centimeter squared. And it likely correlates with the beta morphology, the size, or the spacing. All right, well that brings us to how we can hypothesize the mechanism. Well, the first thing to think about is when our cracked tip is introduced to sodium chloride, your matrix is going to start to dissolve. And that matrix is an aluminum 4 mag. So you're going to see nice, slow, passive dissolution that mildly lowers the cracked tip, maybe to 4 or 5. But this dissolution rate is only 0.1 nanometers per second, while all the crack growth rates that I showed you were 1 to 40,000 nanometers per second. So something else has to be happening in this cracked tip. And of course, we believe it's the beta phase. So when this beta precipitate dissolves, it saturates this cracked tip with aluminum 3 cations and mag 2 cations. These cations undergo hydrolysis and cause the cracked tip pH to go to 2 to 3. This very highly acidic cracked tip then causes cathodic hydrogen production and uptake. And once hydrogen is into the microstructure, it can diffuse to the locations of high stress triaxiality. And so that can be either the matrix and the beta interfaces, or the region between the precipitates where you have constraint between the particles. So you have a nice stress concentration at the edges of the beta, or the region between where you have the constraint. And with the high concentration and the stress in that region, you're able to embrittle the grain boundary. So Beta dissolution acidifies the cracked tip, which promotes hydrogen production and uptake necessary for hydrogen embrittlement of the aluminum boundary. So our question is this hypothesis validated? So let's move on to validate it. I'm going to do that with 4 different experiment procedures. The first is we need to look at Azure C5083. If we are in fact embrittling the region between the beta precipitates, we need to be able to embrittle the Azure C5083 with no beta on the grain boundaries. So the first thing we need to look at is something I've already shown you. I plotted the crack growth rate here, the stress intensity, and the resolution limit. We're going to focus on this red line here, which is right on the resolution limit. That is the unsensitized 5083 with a mass loss of 3 milligrams per centimeter squared in that of sodium chloride at negative 0.8 volts. This is the data that I showed you with the threshold stress intensity. So at 3 milligrams per centimeter squared, you're below that threshold. You are resistant to granular stress corrosion cracking. And we believe this is because that crack tip, acidification is not developed. We are not getting that pH level down to 2 or 3 because we have no beta to cause that dissolution and hydrolysis. So the next thing we decided to do was look at an environment where you have a lot of hydrogen production and that we know causes hydrogen uptake on a bold surface. So we used a sodium hydroxide environment at both open circuit potential and at negative 1.8 volts, very highly cathodic, in a very alkaline solution. These results are plotted here in green. There's actually 2 trends there. And both of these are, as you can see, very resistant to intergranular stress corrosion cracking. And this is likely because we're either not producing the hydrogen production at the crack tip, or maybe there's something blocking the hydrogen from getting in at the crack tip. So we know that we need this acidic crack tip to cause embrittlement. So what can we do to make that crack tip? Acidic crack tip. Well, we came up with 2 different techniques to do this. The first, and both techniques promote the hydrogen production and the uptake. And we can see that because we are seeing very fast crack growth rates. The first one I want to look at is these 2 black trend lines here. We did 2 experiments. Both of these were in a highly acidic aluminum chloride mag chloride environment. And this environment is the predicted environment that we would see in a sensitized crack tip that was actually growing. Now we cathodically polarized this solution and we still saw very high crack growth rates, very low threshold stress intensity and very high crack growth rates. We also ran an experiment in sodium chloride at an anodic polarization, negative 0.73 volts at a neutral pH. And this anodic polarization drove the dissolution of the matrix. So you also see nice cracking, again at relatively high crack growth rates, well above the resolution limit. And we believe that both of these environments cause the hydrogen production because of that acidic crack tip, and that acidic crack tip destabilized the blocking film, allowing uptake. So the first mechanism is validated. We can embrittle the beta-free 5083 as long as we have that acidic crack tip solution. The next thing we want to look at is if we can stifle intergranular stress corrosion cracking in a sensitized microstructure. So specifically, with cathodic polarization, we want to be able to stop the beta dissolution. So I did this, I looked at this experiment with several different polarizations at one sensitization level. And that sensitization was 100 degrees C at 175 hours, for 175 hours, which is about a week. And that gives you a 22 milligrams per centimeter mass loss, what we looked at before. And the exact experiment that I showed you earlier at 800 volts is right here, negative 800 volts. And you can see when you anonically polarize, your crack growth rate increases and your threshold stress intensity decreases. So you're actually getting worse stress corrosion cracking when you anonically polarize. But when you cathodically polarize, you can see that these crack growth rates decrease significantly, but they're still well above the resolution limit. And that's about between negative 900 millivolts and negative 1.2 volts. But once you go down to negative 1.1 and all the way to negative 1.3, you see that you can eliminate the stress corrosion cracking. You are right on that resolution limit. And a better way to look at this is with this plot here. I have your crack growth rate versus your applied polarization. And you can see at the very high potentials, you have very fast crack growth rates. You drop significantly to this region of potentials here, and then you drop to the resolution limit once you're below that potential. Now what's really interesting is these ranges that I've plotted here. This range is the breakdown potential of alpha. And the way we get the breakdown potential of alpha is by looking at these black lines up here. I've plotted a polarization curve for which shows you the potential and the current. This top black line was in sodium chloride. So you can see that at a certain potential, your current takes off. When your current takes off, that means that you're rapidly dissolving alpha. I've also put this in a acidic cracked up solution that's here. So this other blue star shows you that the breakdown potential actually drops. And you have this nice range between a very highly acidic cracked up solution and a neutral solution. Your breakdown potential is dependent on your pH. And I plotted that range here. And you can see that once you get below that breakdown potential of alpha, your crack growth rate drops significantly. So it's basically because we're turning off the dissolution of the alpha phase, or we're making it passive. Now, these next lines is the same thing with beta. You can see that I've taken literature data for the breakdown potential of beta in sodium chloride and the breakdown potential of acidic cracked up solution. And again, I've put that range right here. And once you get below the breakdown potential of beta, your crack growth rate completely goes away, and you're basically eliminating stress corrosion cracking. So to drive this home, when you're above both breakdown potentials, your crack growth rates are very fast. When you're between these breakdown potentials, you only have beta dissolution. Your crack growth rate is slow, but it is measurable. Then when you're below both breakdown potentials, your crack growth rates are pretty much in the resolution limit. And you can see that these also correlate with your pH. All right, so that's our second validation point. Yes, cathodic polarization can promote intergranular stress corrosion cracking resistance. So the next thing we want to look at is if hydrogen charging can cause embrittlement as a function of sensitization. So what we've done here is we've taken several small specimens that are about 2.2 millimeters, and we put them in sodium hydroxide. We've left them there for 16 days, and during that 16 days, hydrogen penetrates the microstructure, and then we load these specimens in air to see if the hydrogen causes embrittlement. And so what I've plotted here is the stress versus displacement during our loading of these specimens. The blue line up here is an uncharged as-received beta-free specimen. And you can see that it broke at a very high stress. When we charged this as-received specimen here, you can see that the stress that it broke at was much lower. So we are in fact embrittling this microstructure just by putting hydrogen in the microstructure. Then when we charge the sensitized specimens, which are these three here, at 22, 50, and 23 milligrams per centimeter squared, our stress at fracture is even lower. So we can absolutely embrittle 5083 with just hydrogen when there's no beta, but this fracture surface is all ductile microvoiding, not intergranular. When you have sensitization, when you have beta on the grain boundaries, you start to see an intergranular fracture. These intergranular regions are very small, but it does fail intergranularly. And this is likely because hydrogen diffuses to the area of high stress triaxiality, and that beta precipitate, just being there, might cause this hydrogen to attract to the grain boundaries. This technique could also be used to characterize beta on the grain boundaries. So since we had these intergranular embrittlements, and it wasn't in a dissolving electrolyte, we still have beta on the grain boundaries when we open these up. So you could be able to see the particles, measure the size, measure the spacing. This technique has a few challenges. left to work out, so we did not focus that on this in this work. Okay, the last thing I want to do is validate this technique is talk about the very rapid crack growth rates that we're seeing in sensitized 5083. And to do that, I need to start by introducing a model. So this plot was put together by Professor Gangbach. He took stage 2 crack growth rates of several high-strength alloys, nickel, aluminum, iron, titanium, all of them loaded in chloride solution, and he plotted these crack growth rates, the fastest measured, against their hydrogen diffusivity. And you can see that all of these crack growth rates correlate very well with their hydrogen diffusion rates. So that means that these rates are likely hydrogen diffusion limited. This trend line here can be modeled, can be explained by this model below. It tells you that your crack growth rate is a function of your hydrogen diffusivity, a critical fracture distance, your concentration of hydrogen at the fracture process zone that is required to cause embrittlement, and the hydrogen concentration at your fracture process zone. So when this inverse squared error function goes to 1, this ratio is about CH sigma equals about 6 to 7 times CH crit. So if we put this to 1, we can draw this trend line, and our X crit will be about 0.9 microns. So the critical distance, fracture distance, for all of these alloys, we have modeled to be 0.9 microns. Now to use this model for our data, we need to figure out what the hydrogen diffusivity is of 5083. And luckily, Professor Scully and Dr. I have measured this diffusion distance for 5083 and found that it's 10 to the negative 10 centimeters squared per second and is independent of the sensitization. So I plotted our data, our unsensitized crack growth rates, right here at 10 to the negative 10. And you can see that the stars are the acidic crack tip solution. This square is the anionic polarized NaCl. And the two triangles are the two resistant experiments. So in the sodium chloride at near open circuit potential and the sodium hydroxide. Now what's interesting is our two highly, very fast, susceptible crack growth rates lie right on this line. So that tells us that we are likely limited by hydrogen diffusion, our crack growth rates are. When this falls below the line, that means that this term is taking over. Our hydrogen concentration at the fracture process zone is likely close to or below the critical concentration required for embrittlement. Now the problem comes when we plot our sensitized data. I have all of the data at near open circuit potential, and sodium chloride is the gray square, and that's well above this trend line. And then all of the polarization data is in these circles. And you can see the anodically polarized data is above the line, and all the cathodically polarized data is below the line. And again, we can use this to explain the data below the line, but we can't necessarily use that for above the line. And that is because if we're assuming that our hydrogen diffusivity is 10 to the negative 10, this inverse error function term squared will only provide 5 to 10 times increase in the crack growth rate, just by the nature of this error function term. So even if we put in 1,000 times hydrogen concentration, more than we need, we'll still only get 5 to 7 times increase. So that'll only put you about here. That won't give you the 2 orders of magnitude increase. So the other term that we might be able to modify is X crit. Now, if X crit is usually a function of fracture mechanics, but if we thought it had to do with the microstructure, it might be due to the beta spacing. So if we wanted to look at 300 nanometers, which is roughly the beta spacing, as Verbalis has shown us, that's this line here. And you can also see that wouldn't explain the very high increase. We would need an X crit of about 2 nanometers, right here, to explain that very rapid crack growth rate. And there's no reason that that microstructure would cause an increase that high. I'm sorry, such a small X crit. So we need to look at other reasons why we are seeing these rapid crack growth rates? Well, of course, it might be because of the beta phase. Is the beta phase dissolution causing these rapid crack growth rates? Well, Ford has done a model to predict the intergranular stress corrosion cracking rates using a slip dissolution of a bare surface aluminum 7 mag alloy. And he found that the maximum crack growth rate occurs at 80 nanometers per second when your current density is about 0.2. Well, we're looking at crack growth rates that are about 10 to the fourth. So this model is likely not going to help us either. If we wanted to look at the current density for these crack growth rates, that would correlate, the current density that would correlate with these crack growth rates, we would need 20 amps per centimeter squared. And you can't get that in the occluded crack tip because of your IR or ohmic drop limitation. We also can't beta can't also cause a mechanical contribution because beta is so small and the spacing is so wide. These beta particles are about 50 to 200 nanometers, and their spacing is about 2 every micron squared. So if we had as much beta as we could, at these sensitization levels, this beta is likely not causing the mechanical fracture. Also, the fracture toughness in air actually increases with sensitization. So the more beta you have on the grain boundary, the higher your fracture toughness is. So we can't really explain this model using those 3 contributions. We have to go back to the hydrogen diffusivity. So when Professor Scully and Dr. I measured these hydrogen diffusivities at 10 to the negative 10, they also saw that when they increased the hydrogen coverage at the traps, your hydrogen diffusivity increased. So you went to a 10 to the negative 10 centimeters squared. And that's likely because you're either saturating or you're filling those traps. So we considered, what if there's no traps in the microstructure? What could your fastest hydrogen diffusivity be in aluminum alloys? And that is about 10 to the negative 7 centimeters squared per second. So we plotted our sensitized data at this point, and we noticed that this fit very well. But how can you actually explain this very rapid crack growth rate? So our theory is that when you load this specimen, the crack tip forms a low energy dislocation structure. All of the dislocations go to this lead structure, which is about 50 nanometers or 500 nanometers to a micron. And these dislocations go to the walls of the structure and leave the center free of trap sites, free of dislocations. Now our beta spacing is about 300 nanometers, so our spacing, or the ligaments between beta, are smaller than that lead structure. So your hydrogen diffusivity within that lead could actually be upwards of 10 to the negative 7 centimeters squared per second. So this would tell us that the local dislocation density is uniquely controlled by the beta spacing. Of course, this is speculative. So that helps us validate the last point, that a more rapid hydrogen diffusivity is likely associated with a local reduction in hydrogen trapping when the beta interfaces or trap sites saturate. And this beta-free ligament size impacts the dislocation structure. All right, well that brings us to our last section, and that's how we can generate a framework to quantify crack growth rates. Sorry that that's covered. So Professor Kelly helped me predict the ohmic drop at the crack tip for all of the experiments that I ran in this work. And we did this by first establishing a pit stability criterion. Basically, your corrosion or your pit will grow if you have a combination of current and diffusion distance high enough or above your pit stability criterion. So once that was established, or once we established that that was occurring in our crack tip, because we were getting intergranular corrosion, we could use the dislocation or the dissolution current density at the tip, which was given to us by our intergranular corrosion rate, and our passive current density on the flanks, which is our matrix, to predict the ohmic drop that was occurring from the bulk applied polarization to your cracked tip polarization. So knowing that difference, you can predict what the potential is at the tip, and you can also predict the pH at the tip. Knowing the potential and pH of the cracked tip, you can get the overpotential for hydrogen production. And this overpotential for hydrogen production is very important because this establishes the concentration of hydrogen at the surface of your cracked tip. Using this relationship and a stress term, we can figure out what the concentration of hydrogen is at the fracture process zone. So that can go right into our model equation. So using this model, I kind of back calculated to see if we could actually predict these crack growth rates. And I want to start with Azure C of 5083. I was able to predict the ratio of hydrogen concentration at the fracture process zone to the concentration that's required at the fracture process zone to cause fracture or intergranular stress corrosion cracking. And I plotted that against our predicted overpotential. And you can see that the trend is very nice. We have an exponential decay as long as we're assuming that the hydrogen diffusivity is 10 to the negative 10 and our critical diffusion or critical fracture distance is 0.9 microns. I did the same thing with all of our sensitized data in sodium chloride polarized. And again, as your concentration of hydrogen decreases, your predicted overpotential, the magnitude of your predicted overpotential decreases. Nice exponential function. As long as our hydrogen diffusivity is 10 to the negative 7, and our X crit is 0.9 microns. So with that, we can show that crack growth rate is controlled by your hydrogen diffusivity, as well as your crack tip chemistry. And these are my conclusions. I can walk you through them. As 5083 is susceptible to severe intergranular stress corrosion cracking by sensitization at 60 to 100 degrees C, specifically in this orientation. Your susceptibility quantitatively correlates with your G67 mass loss. You have a threshold of about 10 milligrams per centimeter squared. Our proposed mechanism of cracking is beta dissolution, hydrogen uptake diffusion, and interbeta ligament hydrogen embrittlement. And we validate it with four different ways. And we can also quantify, we can predict crack growth rates by quantifying the crack tip chemistry and the hydrogen overpotential. And interestingly, we can use cathodic polarization and fracture mechanics, life predictions, to manage structural integrity. So I wanted to conclude by thanking several people. Of course, my research sponsor, Dr. Aaron Perez, at the Office of Naval Research, my advisor, Richard Gangloff, my committee. Thank you all so much for listening to this and helping me out. My mentor at NRL, where I did most of the fracture photography that wasn't presented in this slideshow. Of course, Mary Lynn and Dr. Alyssa Miller, who very much helped me with the electrochemistry. And then fracture group, all of you at CEAS, thank you for coming. Family and friends. Leave conclusions up. Thank you very much.
Thank you. All right, thank you, Cortney. So questions from the audience?
So my first question is, you kept talking about the resolution limit and how it, I guess, told you what was SEC cracking and what wasn't SEC cracking. I was wondering if you'd go into like how you know that. Just like what's so important about the resolution limit? Like how you said it.
Okay, so I just ran a test in air, and I measured the crack growth rate when this test was in the air. So basically in air, you shouldn't be getting stress corrosion cracking unless you're getting hydrogen into the microstructure. So you absolutely could be getting stress corrosion cracking due to moist air, but that's going to be the low level. You could also be getting plasticity that causes an increase in the DCPD, and you could also be getting creep. So those three things could be happening in air. They could also be happening during the test. So we're assuming that our resolution that we can limit our stress corrosion cracking by is due to those crack growth rates, due to those three things. Does that make sense?
Other questions? Going once.
I may have missed it. Is there like any real physical meaning of the X crit, or is it just a kind of
So,
affiliate number?
yeah, X crit is usually the maximum stress ahead of the crack state. So, I have a drawing on that slide. It's usually what it's attributed to. In this model, we basically just, since it fit the data, we put it here. But in fracture mechanics, you'll have a nice stress gradient in your crack tip that's controlled by your stress level, your microstructure. A lot of different things go into the X crit. But this could be one of the main reasons that you have that high stress there. So you're going to have maximum stress at this point. So once you put hydrogen in there, your grain boundaries will break.
Anything else? Okay, let's thank Cortney one more time. And everyone is welcome to leave or stay, but except for the committee, they have to stay.